So a random variable is simply a function from the sample space to the real numbers. To define a random variable, I need an experiment, I need a sample space, I need events, and I need a probability measure that assigns probability to each event. Then a random variable is simply a function from S to R. Now, once I have such a setup, an experiment, sample space, events, and a probability measure, there is nothing to stop us from defining several random variables. That is, defining several different functions from S to R. So based on the experiment, we can define n random variables. It is common then to use a subscript to distinguish them, x1 through xn. And these are simply n different functions, each with the domain S. Each of these random variables may be discrete, continuous, or neither. So I can have a mixture, so it's possible to have a mixture of discrete and continuous random variables. As a concrete example, suppose that I toss 2 dice, then I can define several random variables based on such an experiment. For example, x1 could denote the outcome of the first die, x2 the outcome of the second. I could define a third one, being the sum, and so on. Here is a simple example. I have an experiment. My sample space consists of alpha, beta, gamma, and theta. Each outcome is equally likely. I consider all 16 possible events. I can define my first random variable, call that x. And this is defined by mapping alpha to 2, beta to 2, gamma to 2, and theta to 0. I can define a second random variable, which I here call y, and this is defined by mapping alpha to 0, beta to 1, gamma to 1, and theta to 1. So what's happening here is that this is my sample space. I have 4 different possible outcomes. Chance or nature or whatever you want to call it will pick one of these outcomes according to the probability measure. Once chance has done its job, for example by picking beta, then simultaneously x will take the value 2 and y will take the value 1. So its important point here is that both of the random variables are based on the same experiment. And once the outcome is revealed, the value of each random variable is determined. So if I have 2 random variables, x and y, then an expression which looks like this, the collection where the random variable x takes the value lowercase x, comma, random variable y takes the lowercase y, will be an event. It's a subset of the sample space, and this particular subset contains all outcome that x will map into lowercase x and y will map into lowercase y. So this thing here is an event. Exactly which elements are in the event depends on which values lowercase x and lowercase y takes. Continuing our example, let's consider the event capital X equal to 2, capital Y equal to 1. So now I just have to go through all possible outcomes and see if I can find anyone that X will map to 2 and Y will map to 1. So let's look at them. Alpha will not work. Even though X maps alpha to 2, Y will map it to 0. And it's an AND statement. Both of them must work. Beta will work on the other hand. X will map beta to 2 and Y will map it to 1. Gamma will work as well, while theta will not. So the event x equal to 2, y equal to 1 is exactly the event consisting of the outcome beta and gamma. Just one more example. The event x equal to 0, y equal to 0. Even though it is possible for x to take the value 0 and it is possible for y to take the value 0, it is not possible for this to happen simultaneously. There is no outcome for which both x and y will map the outcome to 0. So this will be the empty set. So realizing that an expression such as this one, x equal to 2 and y equal to 1, is an event, allows us then to define the probability of this. So by p x equal to x and y equal to y, we simply mean the probability of this particular event. We have a probability measure which will assign a probability to each event, so we know that this must exist. Continuing with our example, if we look at the probability of the event x equal to 2 and y equal to 1, we know that the event x equal to 2, y equal to 1 is the same as the event consisting of beta and gamma. And if the probability measure is such that each outcome is equally likely, then I have an event with 2 outcomes out of possible 4. So this probability must be 2 over 4 or 1/2. Similarly, the probability that x is equal to 0 and y is equal to 0 is the same as the probability of the empty set, so that must be 0. We can define events using inequalities as well. So an expression such as this will be an event that will consist of all outcomes that the random variable x will map to a number less than 3 and the random variable y will map to a number less than 1. I can mix inequalities and equalities, and I can have an upper and a lower bound for a random variable. So here's an example: the probability that x is less than 2 and y is greater than 0. Well, all we have to do is again just go through all of the possible outcomes and see which ones satisfy this condition. So we want x to be less than 2 and y to be greater than 0. Alpha does not satisfy this. It's enough to check the x random variable, the same with beta, the same with gamma. However, for theta, x will map that into a number less than 2 and y will map it into a number greater than 0. So theta is in this event, and that's the only one. So that's the same as the probability that the outcome will pick theta. Equally likely, then that's 1 over 4. So it's pretty straightforward to extend this whole idea of events and probabilities to cases where we have more than 2 random variables. So if I have in general n random variables, then I can consider an expression such as this. That's the probability that the first random variable takes the value lowercase x1 and so on. This expression will depend on n variables, x1 through xn. And we simply define it as the probability of this particular event. When we have several random variables, we are still allowed to make these equalities into inequalities.